Somewhere beyond the edge of our star's magnetic bubble, a small spacecraft is coasting through the dark at more than 15 kilometers per second. It carries a golden record, a message to nobody in particular, and a fading heartbeat of plutonium that will fall silent within the next decade. After that, Voyager 2 will keep moving. It will keep moving after our species is gone, after the sun has swelled into a red giant and collapsed into a white dwarf, after the familiar constellations have scrambled beyond recognition, after the Milky Way itself has merged with Andromeda. 1 trillion years from now, that spacecraft, or whatever is left of it, may still be traveling, and almost every map humanity used to describe where it was going will no longer exist. If these are the kind of explorations you enjoy watching, tapping the like and subscribe buttons really helps this channel grow. Now, are you comfortable? Let's begin. Let's start with where Voyager 2 actually is, because the geometry matters for everything that comes next. As of the middle of 2026, the spacecraft is roughly 136 astronomical units from the Sun. That number, 136, is the distance in multiples of the average distance between Earth and the Sun. So the spacecraft is more than 130 times farther from the Sun than we are. Light from the Sun, traveling at 300,000 kilometers per second, takes about 19 hours to reach it. When mission controllers at the Jet Propulsion Laboratory in Pasadena send a radio command up to the spacecraft, they wait roughly 19 hours for that command to arrive, and then another 19 hours for any response. A conversation with Voyager 2 is a 2-day affair. There is no faster way to talk to it. There will never be a faster way to talk to it. That is simply the speed of light and the size of the gap between us. The spacecraft is moving away from the Sun at about 15 1/3 kilometers per second, measured relative to the Sun itself. In more familiar terms, that is roughly 34,000 miles per hour. If you could hold that speed constant and point it at the nearest star system, Alpha Centauri, which sits a little over 4 light years away, the trip would still take you on the order of 80,000 years. Voyager 2 is not aimed at Alpha Centauri. It is aimed, more or less, at a small southern constellation called Pavo, the Peacock. That is the direction the spacecraft is currently heading. Not toward any specific star in Pavo, just in the general direction of that patch of sky, angling downward out of the plane of the solar system on a path the engineers chose decades ago because it was the only way to give the spacecraft a shot at flying past Uranus and Neptune before leaving forever. That downward angle is important. Voyager 1, the elder sibling, is heading roughly upward out of the solar system's plane. Voyager 2 is heading roughly downward, and this asymmetry is the direct fingerprint of the Grand Tour trajectory that made the mission possible in the first place. The two probes took different paths because they had different planetary flyby assignments. Voyager 1 got Jupiter and Saturn, and after Saturn, its trajectory kicked it up and out of the ecliptic plane. Voyager 2 got Jupiter, Saturn, Uranus, and Neptune, and after Neptune, its trajectory kicked it down and out. Each planet the spacecraft passed gave it a gravitational shove, redirecting its path and changing its speed. By the time Voyager 2 was done with Neptune in 1989, its heading was locked in, pointed at Pavo, moving fast, never to return. That last sentence deserves a bit more unpacking, because the Grand Tour trajectory is one of the most elegant pieces of astrodynamics in the history of spaceflight, and understanding it clarifies why Voyager 2 is heading exactly where it is heading and not somewhere else. The core insight, worked out by a young mathematician named Gary Flandreau at the Jet Propulsion Laboratory in the mid-1960s, was that during a narrow window in the late 1970s and early 1980s, the 4 outer planets would happen to be arranged in a rough curve on the same side of the Sun. A single spacecraft, if launched at the right moment on the right trajectory, could use the gravity of each planet to redirect its path toward the next one, gaining velocity at every stop. Without those gravity assists, a mission to Neptune using 1970s rocket technology would have taken something like 30 years. With them, it took 12. Each gravity assist works by the same principle. The spacecraft falls toward a planet, whipping around it in a hyperbolic arc, and emerges on the other side moving in a different direction and, if the geometry is right, at a different speed relative to the Sun. The planet loses an infinitesimal amount of orbital energy in the exchange, so small that it is completely undetectable, and the spacecraft gains a huge boost. At Jupiter, Voyager 2 picked up roughly 10 kilometers per second. At Saturn, it picked up another 5. At Uranus, another 2. And at Neptune, the final gravity assist did not so much accelerate the spacecraft as bend its path, sending it plunging steeply below the plane of the solar system in exactly the direction of Parvo. That final bend at Neptune is the reason Voyager 2 is heading downward now. If the mission planners had chosen a different trajectory past Neptune, the spacecraft could have been sent in any of several other directions. There was a real choice made decades ago about which patch of sky Voyager 2 would coast toward for the rest of its existence. The choice was constrained by mission priorities. The team wanted to fly past Neptune's moon Triton, which required a specific approach geometry, and Triton's flyby then determined the outbound direction. The result is that Voyager 2's current heading toward Pavo is, in a very real sense, a fingerprint left by a single close encounter with a large icy moon in August of 1989. There is something worth pausing on in that fact. The trajectory that will carry Voyager 2 through the next 100,000 years, the next million years, the next billion, was locked in during a period of a few hours in the late 1980s by a small team of engineers who chose to prioritize one particular scientific observation. Nobody at the time was thinking about what star the spacecraft would drift near in 40,000 years. Nobody was thinking about which region of the galaxy it would eventually orbit in. The choice was made for immediate scientific reasons. Get the best possible look at Triton. And the deep time consequences were essentially an accidental byproduct. This is worth remembering when we start thinking about destinations later in the episode. The spacecraft was never really aimed at anywhere in the deep future. Its heading is a residue of decisions made about the near future, extrapolated forward by inertia into a timescale that nobody at the time was actually considering. The other number worth pinning down before we go anywhere else is the moment the spacecraft crossed a threshold called the heliopause that happened on November 5th, 2018. The heliopause is not a wall or a fence. There is no ribbon strung across space marking it. It is a boundary defined by 2 competing pressures. The outward push of the solar wind, which is a thin stream of charged particles flowing off the sun's outer atmosphere, and the inward push of the interstellar medium, the equally thin sea of gas and dust and cosmic rays that fills the space between stars. Where those 2 pressures balance, you get a boundary. Inside that boundary, you are inside the sun's magnetic bubble, called the heliosphere. Outside it, you are in interstellar space proper, Voyager. Two crossed that boundary in 2018, and its instruments recorded the change in real time, a sudden shift in the density and temperature of the charged particles surrounding it. Now, here is the part that gets misreported constantly. Crossing the heliopause did not mean leaving the solar system. It did not mean escaping the sun's gravity. It did not mean escaping the Milky Way. It meant only that the spacecraft passed from a region dominated by the sun's magnetic field to a region dominated by the interstellar magnetic field. The sun's gravity, which is what actually holds the solar system together, extends much, much farther than the heliopause, roughly 1,000 times farther in fact. The outer edge of the sun's gravitational influence is thought to lie somewhere between 100,000 and 200,000 astronomical units. An enormous, poorly defined region of icy debris called the Oort cloud, which is where most long-period comets originate. Voyager 2 is nowhere near the outer edge of the Oort cloud. It is only at about 136 astronomical units. The spacecraft, moving at its current speed, will take approximately 30,000 years to pass through the Oort cloud entirely and reach a region where the sun's gravitational grip finally becomes negligible. Hear that number again. 30,000 years just to get out of the sun's gravitational neighborhood. And that is only the first step of the story we're trying to tell. But long before Voyager 2 reaches even the outer Oort cloud, something more immediate will happen. The plutonium will run out. The power source on board is a device called a radioisotope thermoelectric generator, usually shortened to RTG. Voyager 2 carries 3 of them, mounted on a boom that sticks out from the main body of the spacecraft to keep them from cooking the electronics with their heat. The way an RTG works is very simple, and that simplicity is exactly why it is trustworthy. You take a lump of plutonium-238, which is a radioactive isotope that decays by emitting alpha particles. That decay produces heat. Quite a lot of heat, actually. You surround the lump with an array of thermocouples, which are metal junctions that generate a small electrical voltage when one side is hotter than the other. The hot side is the plutonium. The cold side is the surrounding vacuum of space. The temperature difference produces electricity. There are no moving parts, nothing to break, nothing to lubricate, nothing to wear out. You just have a slowly cooling lump of radioactive metal quietly powering the spacecraft for decades on end. The catch, and it is a catch that was built into the mission from day one, is that plutonium-238 has a half-life of about 88 years. That means every 88 years, half of it is gone, transmuted into non-radioactive daughter elements. The electrical output drops accordingly. When Voyager 2 launched in 1977, its 3 RTGs together produced about 470 watts of electrical power. That is roughly the same as 4 or 5 old-fashioned incandescent light bulbs. It was not much, but it was enough to run the spacecraft's computers, the radio transmitter, the heaters, and a whole suite of scientific instruments. Today, nearly 5 decades later, the output is down to a bit under 250 watts, and it drops by about 4 watts every year. That is why the mission has been undergoing what engineers politely call instrument turn-offs. Over the past several years, the team at JPL has been sequentially shutting down instruments on Voyager 2, one by one, to keep the essential systems running. In 2024, they turned off the plasma science instrument, which had been operating for 47 years and had provided the definitive measurements of Voyager 2's crossing of the heliopause. In 2025, they shut off more. The instruments still running as of this recording are a small handful. A magnetometer, a low-energy charged particle detector, a cosmic ray subsystem, and a plasma wave subsystem. That is it. Everything else has been powered down, either because it broke, or because it was on a moving platform that no longer moves, or because the engineers had to sacrifice it to keep the more important instruments alive. And the shutdowns are not going to stop. Every year, another 4 watts disappear. Every year or two, another instrument has to be turned off. NASA's official estimates have shifted over time, but the current expectation is that Voyager 2 will lose the ability to run any science instruments at all sometime around the end of this decade, or perhaps a couple of years into the next one. After the science instruments are gone, the engineering team can keep the radio transmitter alive for a while longer by running down the remaining power reserves, but eventually, probably in the 2030s, even that will fail. The signal will go silent, the last commands will be sent, there will be no response, and the mission, in the formal, institutional, funded, human-in-the-loop sense, will be over. That moment is worth pausing on, because it is one of the strangest transitions in the entire story of spaceflight. When a car breaks down, it stops. When a ship sinks, it goes to the bottom. When an airplane crashes, it comes to rest. When a spacecraft in interstellar space runs out of power, it does not stop. It doesn't slow down. It does not fall. It doesn't go anywhere different than it was going before. It just keeps going in exactly the same direction, at exactly the same speed, forever, or as close to forever as any physical object can manage. Voyager 2, once it goes silent, will still be moving at more than 15 kilometers per second. The plutonium will keep decaying, producing less and less heat every year, and eventually the internal temperature of the spacecraft will drop toward the temperature of the interstellar medium, which is only a few degrees above absolute zero. The computers will freeze, the propellant, if any remains, will freeze, the lubricants in whatever mechanical joints still exist will freeze, but none of that will slow the spacecraft down, because there is nothing out there to slow it down. Interstellar space is not empty, but it is close enough to empty that the friction on a car-sized object moving at 15 kilometers per second is unmeasurably small on any human timescale. This is the moment where the mission ends and something else begins. It is the moment where Voyager 2 stops being a spacecraft, in the operational sense, and starts being an artifact. A piece of coasting metal, a relic. It will still have the golden record bolted to its side. The 12-inch phonograph disc engraved with sounds and images from Earth. A message intended for any intelligence that might ever come across it. It will still have the aluminum cover on that record, etched with a diagram showing our sun's position relative to 14 pulsars, so that a hypothetical finder could triangulate where the spacecraft came from. It will still be, in every physical particular, the object that left Earth in 1977. But there will be no one home. The lights will be out. And nobody on Earth will know exactly where it is anymore. Because tracking it requires a radio signal, and the radio signal will be gone. That last point is worth dwelling on for a moment, because it is not obvious. As long as Voyager 2 is transmitting, the Deep Space Network, a set of enormous radio dishes distributed around the globe, can pinpoint its location extremely precisely by measuring the direction the signal comes from and the tiny Doppler shift in the signal's frequency. Once the transmitter dies, all of that goes away. The spacecraft becomes invisible. Even the most powerful optical telescopes we have cannot resolve a car-sized object at a distance of 150 astronomical units. The James Webb Space Telescope, for all its extraordinary power, is designed to see faint galaxies billions of light years away, not dark objects a light day away. And by the time Voyager 2 goes silent, it will not be at 150 astronomical units anymore. It will be somewhere out around 160 or 170, and in the decades and centuries after that, it will just keep receding. So, the answer to where is Voyager 2 right now is actually more nuanced than it sounds. Right now, in 2026, we know where it is to within a few kilometers, because it is still talking to us. In 2035, when it may have gone quiet, we will know its last confirmed position and its last confirmed velocity. And from those two pieces of information, we can extrapolate forward for a while with reasonable confidence. But every year that passes after the transmitter dies, the uncertainty in our knowledge of its position grows. Small perturbations from things we cannot easily model, the pressure of interstellar dust grains against the spacecraft's surface, the gentle tug of gas clouds it drifts through, the drift of the sun's own motion through the galaxy, begin to accumulate. Not enough to matter for a decade, not enough to matter for a century, but over thousands of years, and then millions, and then billions, those tiny uncertainties compound into a fog of possibility that grows larger the further out you try to look. That fog is the reason we cannot answer the title question with a specific coordinate. It is not because we lack the mathematics. It is not because we lack the physics. It is because the physics itself has an uncertainty built into it that grows with time, and 1 trillion years is a very, very long time. Before we leave this first part, there is one more thing worth establishing about the present moment, because it will matter for everything that follows. Voyager 2 is not moving alone. It is embedded in a much larger moving system. The Sun itself is moving, orbiting the center of the Milky Way at roughly 230 kilometers per second. More than 15 times faster than Voyager 2 is moving relative to the Sun. The entire solar system, Sun and all the planets and Voyager 2 included, is on a long, slow lap around the galactic core. A single orbit that takes approximately 225 to 250 million years to complete. That interval is sometimes called a galactic year. Since the Sun formed about 4.5 billion years ago, it has made roughly 20 of these laps. Voyager 2, from the perspective of the galaxy, is not so much heading toward Pavo as it is riding along with the Sun on its current lap, while also drifting slowly in the general direction of Pavo relative to the Sun. This distinction is going to become crucial when we start talking about deep time trajectories. The spacecraft has not escaped the Sun's gravity. It has not escaped the galaxy's gravity either. It cannot, actually, because it is not moving fast enough. To escape the Milky Way entirely from our current location, an object would need a velocity of somewhere around 550 kilometers per second. The galactic escape velocity, and Voyager 2, riding along with the Sun at 230 kilometers per second, plus its own additional 15 relative to the Sun, does not come anywhere close. Even in the most favorable direction, it falls short of galactic escape by hundreds of kilometers per second, which means, put simply, Voyager 2 is going to keep orbiting the center of the Milky Way for as long as the Milky Way exists in a form recognizable as a galaxy. It is not headed out into intergalactic space. It is a satellite of the galaxy, and it always will be, at least until something else happens to it. And we will get to what those something else's might be. So the picture we are ending with for this stage of the story is this. A dying spacecraft, currently about 19 light hours from us, coasting outbound through the outer heliosphere and into interstellar space, aimed at Parvo relative to the Sun, but really riding along with the Sun on a much larger galactic orbit. Its instruments are being shut off one by one. Its plutonium is running down. Within a decade or so, the last watt of usable electricity will drain out of it. The transmitter will fall silent, and we will lose the ability to track it directly. From that moment forward, it will still be moving, still coasting outbound, still carrying its golden record, but nobody on Earth will hear it anymore, and the fog of positional uncertainty will begin to grow. That is the state of the object, right now, on the eve of its transition from spacecraft to artifact. Everything that comes after this is a story about inertia, gravity, and time, with almost no additional human involvement possible. We have already essentially done everything we are ever gonna do to Voyager 2. The last course correction happened decades ago. There will be no more. The spacecraft's future path is already written into its momentum and the gravitational field of the galaxy it is embedded in. All that is left to do is wait and calculate and admit at the end of the calculation how much of the answer we cannot know. Before we can talk about 1 trillion years, though, we have to talk about a much smaller number, the tens of thousands of years, and then hundreds of thousands, during which Voyager 2 will pass close to the first of many stars whose names we currently know. And it turns out that even at those relatively modest timescales, the map begins to change under the spacecraft's feet in ways that most people never think about. Because the stars, it turns out, are not fixed. They move too. And they move fast enough that even before Voyager 2 reaches its first projected stellar encounter, the sky it is moving through will already look different from the sky we see tonight. That is where we're going next. The last radio contact with Voyager 2 will happen quietly. There will not be a dramatic final transmission. There will not be a farewell message. There will be, at some point in the 2030s, a scheduled communication pass during which the deep space network's antennas will listen for the faint carrier signal from the spacecraft. The same faint carrier signal they have been listening for across nearly 5 decades. And this time, they will not hear it. Or they will hear something so degraded, so buried in noise, that the engineers will look at each other and confirm what they already suspected. The power is gone. There's nothing left to say. What happens next, from the spacecraft's own point of view, is nothing. Absolutely nothing. There is no sudden change, no dramatic shift in motion, no perceptible transition from a functioning probe into a piece of drifting hardware. The last watt of electricity trickles out of the plutonium. The last heater switches off. The last capacitor discharges, and Voyager 2 keeps moving at exactly the same speed, and in exactly the same direction it was moving the second before. The physics of coasting objects in near vacuum is astonishingly boring, and that is precisely what makes it so consequential over long timescales. There is no friction to slow the spacecraft. There is no atmosphere to erode it in any meaningful hurry. There is no fuel to burn or run out. Inertia, once granted, is never revoked. It is simply carried forward until something else acts on it. And in interstellar space, the things that act on it are very, very small. Let's take stock of the forces that will actually influence Voyager 2's motion after it goes silent. The dominant one, by an enormous margin, is gravity. The spacecraft is deep inside the gravitational well of the Milky Way, and the Milky Way's gravity dictates its long-term orbit around the galactic center. Nested inside that is the Sun's own gravity, which, as we established earlier, extends far beyond the heliopause and continues to weakly pull on Voyager 2 for tens of thousands of years to come. Nested inside that, over even smaller regions, are the gravitational fields of individual nearby stars, most of which are too far away to matter at any given moment, but a few of which will occasionally pass close enough to give the spacecraft a tiny nudge. Beyond gravity, there is the interstellar medium itself. This is the near vacuum between stars, but it is not a perfect vacuum. It contains, on average, roughly 1 atom of hydrogen per cubic centimeter, along with trace amounts of helium, a smattering of heavier elements, and a fine haze of dust grains. When Voyager 2 moves through this medium at 15 kilometers per second, individual atoms and dust grains do collide with its surface. The result is a slow process called sputtering, in which atoms of the spacecraft's outer material are gradually knocked loose by these impacts. The rate is astonishingly slow, on the order of a few atomic layers per million years. But over billions of years, sputtering is not negligible. It is one of the mechanisms that will eventually make the physical surface of the spacecraft look different from the way it looked at launch. There is also cosmic radiation. High-energy particles from distant supernova remnants and other astrophysical sources pass through the spacecraft constantly, doing tiny amounts of damage to the material every time. And there is a very slight drag from the interstellar medium as a whole. Though on Voyager 2's mass and cross-section, that drag is essentially negligible over any timescale short of 1 billion years. All of these forces exist. Most of them do not matter yet. What matters, for the first several 100,000 years after Voyager 2 goes silent, is stars. Specifically the fact that Voyager 2 is going to pass reasonably close to a few of them. The first such encounter, based on current trajectory projections, will happen roughly 40,000 years from now. The star involved is called Ross 248, a small dim red dwarf in the constellation Andromeda. Right now, Ross 248 sits about 10 light years from the Sun. It is not moving away from us, it is actually moving toward us at a modest pace. And Voyager 2, coasting outbound in its slightly downward direction, will pass through the general region of space where Ross 248 is heading. The projected closest approach is somewhere around 1.5 light years. That is not close in any human sense of the word. 1.5 light years is more than 9 trillion miles, but in stellar terms, it counts as a genuine flyby. Nothing dramatic will happen during this encounter. The star will not capture Voyager 2. Its gravity is far too weak at that distance to redirect a coasting object meaningfully. The spacecraft will experience the slightest of gravitational tugs, altering its trajectory by an amount that would be difficult to measure even if anyone was still measuring. Then Ross 248 will continue on its own path, and Voyager 2 will continue on its slightly altered one, and the two will drift apart forever. But notice what the encounter does mean. It means that the spacecraft, moving at 15 kilometers per second, has covered roughly 1.5 to 2 light years relative to nearby stars in 40,000 years. That is the actual pace at which Voyager 2 is traveling through the local stellar neighborhood. Not blindingly fast, not slow, somewhere in the middle, fast enough that it will encounter another star or two within a few 100,000 years, slow enough that it will never catch up to any star system that is moving away from it. And every one of these encounters will be governed by the same underlying reality. The stars are moving too. It is worth putting Voyager 2's projected encounters into context with what its twin is doing, because the comparison illustrates how utterly ordinary a stellar flyby actually looks on cosmic terms. Voyager 1, heading upward out of the ecliptic plane, has its own projected close approach coming in roughly 40,000 years. The star involved is called Gliese 445, currently sitting about 17 light-years away in the constellation Camelopardalis. Gliese 445 is another small dim red dwarf, similar in character to Ross 248, and like Ross 248, it is moving toward the Sun's neighborhood. When Voyager 1 and Gliese 445 reach their closest approach, they will be separated by about 1.5 light-years. Essentially the same distance as Voyager 2's encounter with Ross 248, and at nearly the same time. Two spacecraft, launched from the same launch pad within weeks of each other, will experience their first genuine stellar flybys roughly simultaneously with two completely different red dwarfs on opposite sides of the sky. That is not planning. That is the accidental symmetry of what close encounter means when you are moving at 15 kilometers per second through a stellar neighborhood where the average distance between stars is several light years. There is a broader lesson buried in that symmetry. The reason both spacecraft will have their first close approach at roughly 1.5 light years, rather than something dramatically closer, is that the local stellar neighborhood simply is not dense enough for closer passes to happen frequently. The average spacing between stars in our region of the galaxy is somewhere around 4 to 5 light years. A random object drifting through this neighborhood at Voyager's speed will, on average, come within about a light year of a star every couple of 100,000 years. Closer approaches, passes within a fraction of a light year, happen much less often, maybe once every few million years for a randomly moving object. And genuine near collisions, passes within, say, 1,000 astronomical units, which would be close enough to be gravitationally interesting, happen essentially never on human timescales. Space is very, very empty, and the odds of any specific coasting object encountering any specific star at close range in any given interval are vanishingly small. This is the point where the map begins to fall apart, and it deserves careful attention, because it is one of the most misunderstood aspects of interstellar navigation. When we say Voyager 2 is heading toward the constellation Pavo, we mean that if you stood on Earth today and drew a line from your feet through the center of the Earth and out toward the spacecraft's current direction of motion, that line would end up pointing at a patch of sky that contains the stars we call Pavo. But those stars are not going to stay where they are. The individual stars that make up Pavo and every other constellation are all moving through space independently, each on its own orbit around the galactic center, each at its own speed, in its own direction. Astronomers call this stellar proper motion. It is measured in arcseconds per year, an arcsecond being a very small angular unit, 1/3,600 of a single degree. And for most nearby stars, the proper motion is on the order of a fraction of an arcsecond per year. That sounds tiny, and over a human lifetime, it is tiny. The constellations you see tonight will look essentially identical to the constellations your great-grandparents saw, but over 10,000 years, or 100,000 years, the changes become noticeable. Over 1,000,000 years, the sky rearranges itself so thoroughly that most of the constellations become unrecognizable. The Big Dipper, familiar to every Northern Hemisphere child, will lose its handle, Orion's belt will scatter, and Pavo, the peacock, will no longer be pointed at by any line drawn from Earth today. So what does it mean, in a deep time sense, to say that Voyager 2 is heading toward Pavo? It means that right now, in 2026, that direction points at those stars. It does not mean the spacecraft will actually reach Pavo, or even that Pavo will still exist as a coherent grouping of stars by the time the spacecraft covers any significant fraction of the distance. In 100,000 years, the stars currently in Pavo will have drifted, and Voyager 2 will have drifted, and the two directions of drift will not necessarily coincide. The spacecraft may end up somewhere in the general vicinity of where those stars used to be, but the stars themselves will have moved on. The next major projected stellar encounter after Ross 248 comes much, much later. Around 296,000 years from now, Voyager 2 is expected to pass within about 4 light years of Sirius, the brightest star in Earth's night sky. Sirius is a spectacular target for imagination. It is a young, hot, blue-white star with a white dwarf companion, and it is currently visible in the winter sky as the anchor of Canis Major. 4 light years is a bit farther than the current distance from the Sun to Alpha Centauri, so this is not a close pass either, but it is close enough that the spacecraft will spend a long time, many thousands of years, within a region where Sirius is the dominant nearby star. Again though, notice the caveat. In 296,000 years, Sirius will not be where it is today. Sirius has its own proper motion, and while astronomers have measured it very precisely, the extrapolation carries uncertainty. The current best projection is that Voyager 2 and Sirius will happen to pass within about 4 light years of each other. But that projection is only as reliable as our knowledge of both objects' velocities, and Voyager 2's projected velocity in 296,000 years assumes no significant perturbations along the way. It assumes the spacecraft coasts along without being nudged meaningfully by anything else. Is that assumption safe? Over a few 100,000 years, probably yes. The gravitational perturbations from distant stellar encounters are so small that they accumulate very slowly. But even over that relatively modest timescale, tiny errors in our current measurements of Voyager 2's position and velocity, errors as small as a few meters and a few centimeters per second, grow into uncertainty ellipses that stretch across appreciable fractions of a light year by the time we reach the Sirius encounter. And that uncertainty only grows from there. The word for what is happening here is chaos. Not chaos in the everyday sense of disorder, but chaos in the mathematical sense, in which small differences in initial conditions produce large differences in outcomes over time. Voyager 2's future trajectory is, in principle, entirely deterministic. Given perfect knowledge of the spacecraft's position and velocity right now, and perfect knowledge of every gravitational influence it will encounter, we could calculate exactly where it will be at any future moment. But we do not have perfect knowledge. Every measurement has an error bar. Every model has approximations. And those errors and approximations compounded over hundreds of thousands of years, and then millions and then billions, blur any specific prediction into a cloud of possibilities. For a few 100,000 years, the cloud is small enough that we can meaningfully say, Voyager 2 will pass near Sirius. For a few million years, the cloud has grown large enough that we can no longer meaningfully name specific stars. We can only describe statistical properties, such as the average frequency with which the spacecraft will pass within some distance of some kind of star. For a few billion years, the cloud has grown so large that even statistical descriptions become uncertain, because the population of stars themselves is changing. Some are dying, some are being born, some are being ejected from the galaxy by close encounters with other stars. And for 1 trillion years, the cloud is essentially the whole galactic remnant. This is why the honest answer to where will Voyager 2 be gets progressively harder to give as you look further into the future. It is not that scientists are being cagey. It is that the physics genuinely does not allow a more specific answer beyond a certain time horizon. Let's talk for a moment about what is happening to the spacecraft's physical body during all this coasting. Because while gravity dictates its path, the interstellar medium is slowly doing things to its surface. The most immediate effect is from dust. The interstellar medium contains grains of dust, mostly carbon, silicates, and various ices, ranging in size from individual molecules up to roughly a micron across. At 15 kilometers per second, each of these grains hits the spacecraft with enough energy to vaporize a tiny amount of surface material at the point of impact. The larger grains are rare, and even the small grains are extraordinarily sparse. The average interstellar dust grain density is something like 1 grain per cubic meter for the smaller sizes, and vastly less for larger ones. So the rate of impacts is low, but it is not zero. Over the course of 100,000 years, Voyager 2 will sweep out an enormous volume of space, and it will collect a significant number of small dust impacts along the way. Each impact pits the surface, each pit removes a tiny amount of material. Over 1 million years, the outer surfaces of the spacecraft, the aluminum shielding, the gold coating on the antenna, the exposed metal edges of the various instrument booms will develop a fine texture of microscopic craters. The golden record itself, tucked against one side of the spacecraft and covered with an aluminum cover plate, is somewhat protected, but not entirely. The engineers who designed the golden record calculated that the aluminum cover plate would give the record a projected lifetime of at least 1 billion years against interstellar erosion. That estimate is based on rough models of dust flux and sputtering rates, and it comes with uncertainty. But the general point is that the record was designed to last on geological timescales. Beyond dust, there is cosmic radiation. High-energy particles, mostly protons and helium nuclei accelerated to relativistic speeds by distant supernova remnants, pass through the spacecraft continuously. Each one leaves a tiny track of ionization damage in whatever material it happens to pass through. Over long periods, this damage accumulates. Electronics become degraded. Not that this matters, because the electronics stopped working when the power died, and structural materials become slightly more brittle. Polymers, if any exist on the spacecraft, gradually break down. Metals fare better, but even metals eventually show cumulative radiation damage over billions of years. And then there is the extremely slow process of cosmic ray spallation, in which a heavy cosmic ray particle strikes an atom in the spacecraft's material, with enough energy to fragment the atomic nucleus, transmuting the atom into a different element. This is a fantastically rare event on human timescales, but on billion-year timescales it becomes measurable. The composition of the spacecraft's surface will very slowly shift, atom by atom, over deep time. There is another aspect of the interstellar medium that is worth introducing here, because Voyager 2 is not just moving through a uniform sea of gas and dust. The interstellar medium has structure. It is organized, at least loosely, into regions of different density and composition. The Sun and everything around it, including Voyager 2, are currently embedded in a region called the local interstellar cloud, a small patch of slightly warmer, slightly denser gas, roughly 30 light-years across. The local interstellar cloud is itself embedded in a much larger, much emptier region called the local bubble, a cavity in the interstellar medium about 1,000 light-years across that was probably carved out by a series of ancient supernova explosions millions of years ago. Voyager 2 is currently near the edge of the local interstellar cloud. Astronomers using ultraviolet observations of nearby stars have mapped the boundaries of this cloud in some detail, and the projections suggest that the Sun and its neighborhood will pass out of the local interstellar cloud and into an adjacent structure, sometimes called the G cloud, within the next few thousand years. The G cloud has somewhat different properties. Its gas is slightly denser. Its dust content is measurably different. Voyager 2, moving with the Sun, will experience this transition too. From the spacecraft's perspective, nothing dramatic will happen. The density change is small in absolute terms, but the rate at which dust grains impact the spacecraft, the properties of the interstellar magnetic field it is embedded in, the local density of hydrogen atoms streaming past its surface, all of these will shift slightly as the Sun's neighborhood drifts from one cloud into another. Over long periods, the Voyager 2 will pass through several such regions, each with its own characteristics, and the cumulative erosion history of the spacecraft will reflect that varied journey. The magnetic environment matters too, in a way that is worth spending a moment on. Inside the Sun's heliosphere, the dominant magnetic field is the one generated by the Sun and carried outward by the solar wind. That field forms a spiral shape as the Sun rotates, sweeping the field lines around like water from a lawn sprinkler. Voyager 2 spent 41 years inside that structure, from launch in 1977 until its heliopause crossing in 2018. Now it is outside. The magnetic field surrounding it now is the interstellar field, which is much weaker but also much more uniform and much more ancient. It is the field that permeates the entire local region of the galaxy, generated by the aggregate motion of ionized gas throughout the disk. For a coasting piece of metal, the magnetic environment does not matter much in a mechanical sense. Voyager 2 is not electrically charged in any significant way, and the interstellar field is not strong enough to exert measurable forces on the spacecraft's motion. But the field does have consequences for the surface of the spacecraft over long periods. Charged particles from the surrounding medium, cosmic rays in particular, spiral along magnetic field lines rather than moving in straight paths. The interstellar field determines the direction from which cosmic rays predominantly arrive at the spacecraft. Over billions of years, this affects which surfaces of Voyager 2 receive the most radiation damage, which parts of the spacecraft erode fastest, and how the surface composition slowly shifts from cosmic ray spallation. There is one more feature of the interstellar environment worth noting. Ahead of the Sun, in the direction the Sun is moving through the galaxy, there is a subtle asymmetry in the surrounding gas. A region sometimes described as the outer heliosheath and the bow region beyond it, where the interstellar medium is compressed slightly by the Sun's motion. Voyager 2 crossed through the outer heliosheath before reaching the heliopause, and it is now moving through interstellar gas that has been mildly disturbed by the Sun's passage. Ahead of the spacecraft, in the direction of Pavo, which is not exactly the direction the Sun is moving, but has some component in the Sun's direction of motion, the interstellar medium is a little bit denser than it would be otherwise. The spacecraft will encounter this compressed gas as it moves outward, and the dust flux it experiences will be slightly elevated for tens of thousands of years compared to the flux it would experience in undisturbed interstellar space. These are all small effects. None of them changes the fundamental picture, but they do illustrate that the environment Voyager 2 is coasting through is not featureless. It has structure, and that structure matters over long enough intervals. None of these processes will destroy Voyager 2 within 100,000 years, or 1 million, or 10 million. The spacecraft is fundamentally a chunk of metal, and metal is durable. But the accumulated effects across 1 billion years become significant. And across 1 trillion years, the timescale of our title question, the situation becomes something else entirely, which we will get to in later parts. For now, the picture at this stage of the journey is this. Voyager 2, silent, is coasting through the Sun's outer gravitational neighborhood. It has passed near Ross, 248 at 40,000 years, been imperceptibly nudged, and continued on. It has passed near Sirius at 300,000 years, and again been very slightly nudged. Its trajectory has begun to accumulate small deviations from the projections we made when it was still transmitting. The map of nearby stars has already rearranged itself substantially. Constellations we knew have blurred and reformed. The spacecraft's original heading toward Pavo no longer means what it meant when the trajectory was set. Pavo, as a coherent constellation, no longer exists. Its stars have drifted to different parts of the sky. The spacecraft itself has begun to show the earliest signs of interstellar wear. Its surface bears a very faint texture of microscopic dust craters. Its exposed electronics are radiation damaged to a degree that would have destroyed any functional systems, if any functional systems remained. Its interior is cold, barely above the temperature of the interstellar medium itself, a few degrees above absolute zero. The plutonium in the RTGs continues to decay, but so slowly that it will still be measurably radioactive in 100,000 years, and in 1 million, and even in 10 million. The half-life of plutonium-238 is only 88 years, so after a few thousand half-lives, essentially all of it is gone. But the daughter products of that decay, uranium-234 and thorium-230, are themselves radioactive with much longer half-lives, and the decay chain continues quietly for millions of years. The golden record is still bolted to the spacecraft's side. Its aluminum cover plate has begun to show the same faint dust crater texture as the rest of the exterior surfaces. If anyone could somehow retrieve and open it, the record itself would still be playable. The etched grooves are protected by the cover, and the record's projected lifetime against erosion is measured in hundreds of millions or billions of years. But nobody is coming to retrieve it. There is no one out here. Just the spacecraft and the sparse interstellar medium and the distant stars and the gentle grip of galactic gravity. Meanwhile, on Earth, or on whatever Earth has become, the mission has long since faded from active memory. The engineers who built Voyager 2 are gone. Their students are gone. Their students' students are gone. Even the institutions that funded and operated the mission may have changed shape or ceased to exist. The Deep Space Network antennas may still be pointed at the sky, listening for other missions, but there is no longer any expectation that they will hear from Voyager 2. The spacecraft's last known position, calculated from its final transmission, is preserved in archives somewhere, along with the trajectory projections. Someone occasionally references those archives out of historical interest, but nothing new is being learned about the spacecraft. It has stopped teaching us. It has become something we know only through the residue of what it used to be. And still, out there in the darkness, it moves. 15 kilometers per second, more or less, downward and outward from the plane of the solar system, roughly toward what used to be Pavo, being nudged imperceptibly by every star it passes, being polished imperceptibly by every dust grain it strikes, being irradiated imperceptibly by every cosmic ray that passes through it, and carrying its silent message to no one in particular, forever or as close to forever as the physics allows. But forever, of course, is not the right word, because the story we are telling stretches to 1 trillion years, and long before we get anywhere near that time scale, something is going to happen that will change the environment through which the spacecraft is moving in ways that dwarf everything we have discussed so far. The sun is going to die, and the galaxy the spacecraft is riding in is going to collide with another galaxy. And after that, nothing about the map, nothing at all, will look the way it looks now. That is where we are going next. We have to widen the frame now. Everything we have discussed so far, the crossing of the heliopause, the shutdown of the instruments, the flyby of Ross 248 at 40,000 years, the more distant pass near Sirius at nearly 300,000, all of that fits inside the first million years of Voyager 2's silent existence. A million years is a lot of time by human reckoning. It is roughly 4 times longer than our species has existed. But in the story we are actually trying to tell, a million years is barely a footnote. The interesting timescales, the ones that transform the galaxy through which the spacecraft is moving, are measured not in millions of years, but in billions. And the deepest question of the episode, where will Voyager 2 be at 1 trillion years, sits a full 3 orders of magnitude beyond even that. So let us start pushing the clock forward, and let us start with the Sun. Our star is currently about 4.5 billion years old. It sits in the middle of what astronomers call the main sequence, the long, stable phase during which a star fuses hydrogen into helium in its core and stays roughly the same size, temperature, and brightness for billions of years. The Sun has been in this phase since it formed, and it will remain in it for approximately another 5 billion years. That is the timescale on which the Sun changes gradually rather than dramatically. Over those next 5 billion years, the Sun will slowly brighten. It is already about 30% brighter than it was when it formed, and by the time it reaches the end of its main sequence phase, it will have brightened by another 40% or so. long before then, Earth will have become uninhabitable. The increasing solar output will boil off the oceans and strip the atmosphere, probably within the next billion years, well before the sun leaves the main sequence at all. But the truly dramatic changes come after the main sequence ends. Roughly 5 billion years from now, the hydrogen in the sun's core will finally run out. When that happens, the core will contract under gravity, heat up, and the shell of hydrogen surrounding the core will ignite in a runaway fusion process that swells the sun's outer envelope enormously. The sun will expand into a red giant, a bloated, cool, ruddy star hundreds of times its current diameter. Its outer atmosphere will engulf Mercury, then Venus, and possibly Earth itself. Though the exact fate of our planet is uncertain because the sun will simultaneously be losing mass, which will loosen its gravitational hold on the inner planets and allow their orbits to expand outward. Then, over the following few 100 million years, the sun will go through a series of increasingly unstable phases. It will pulse. It will shed its outer layers into a slowly expanding shell of gas called a planetary nebula. A term that has nothing to do with planets, historically named because early telescopes made these shells look like faint, distant planets. The nebula will glow for tens of thousands of years, illuminated by the exposed core of what used to be the sun, and then it will fade and disperse into the interstellar medium. What remains behind is the sun's core itself, laid bare, an object about the size of Earth, made of carbon and oxygen, packed so densely that a teaspoon of it would weigh several tons. That object is a white dwarf. It is what our sun will become, and it will remain in that form, slowly cooling, for a very, very long time. Voyager 2, throughout all of this, will not care. Let me say that more carefully. Voyager 2, being a coasting object with no functional systems, has no way to be affected by the sun's transformation, except through gravity. And in gravitational terms, the sun's transformation into a red giant and then a white dwarf changes surprisingly little. The mass of the sun does decrease during the red giant and planetary nebula phases, probably by about 40%, ending up as a white dwarf of roughly half a solar mass. That mass loss slightly weakens the sun's gravitational grip on distant objects. The Oort cloud may become partially unbound. Distant comets may drift away. But Voyager 2, by 5 billion years from now, will be so far from the sun that even before the mass loss, it was only very weakly bound gravitationally. The sun's death does not fling the spacecraft anywhere in particular. It just reduces, slightly, the strength of the invisible string that has connected the spacecraft to its origin for billions of years. By the time the sun becomes a white dwarf, Voyager 2 will be somewhere in the range of a quarter to half a light year away. Give or take enormous uncertainty bars. It will still be orbiting the galactic center along the same general path the sun is following, because it is still riding along with the sun's motion through the galaxy. But the connection between spacecraft and star has become tenuous enough that we might reasonably say the spacecraft has now separated from the solar system entirely. There is no more solar system, really. There is a cooling white dwarf, the scattered remnants of the outer planets and Oort cloud, and a whole lot of empty space where the inner planets used to be. Voyager 2 drift through this landscape of ruin without interacting with any of it in a meaningful way. Now let's expand the frame further, because something much larger is about to happen. The Milky Way is not alone in space. It has neighbors, small satellite galaxies orbiting it. And much more importantly, a comparable spiral galaxy called Andromeda sitting roughly 2.5 million light years away. Andromeda is the largest galaxy in our local group, slightly bigger than the Milky Way, containing roughly 1 trillion stars to our galaxy's 400 billion or so. And Andromeda is moving toward us. It has been moving toward us for the entire history of the observable universe, drawn together by mutual gravitational attraction across the intergalactic void. The current best estimate, based on measurements from the Hubble Space Telescope and Gaia observations of Andromeda's motion, is that Andromeda and the Milky Way will begin to interact gravitationally on a serious level somewhere between 4 and 5 billion years from now. That is roughly the same time frame as the Sun's transition into a red giant. Though the two events are unrelated in any physical sense, it is only a coincidence of numbers that they happen at similar times. The interaction between the two galaxies will not be a sudden collision in the way we usually picture collisions. Galaxies are mostly empty space. The individual stars in Andromeda and the individual stars in the Milky Way will almost certainly not collide with each other. Stars are much too small, and the spaces between them are much too large. The odds of any specific star in one galaxy actually striking any specific star in the other are essentially zero. What will happen instead is a slow gravitational dance. The two galaxies will interpenetrate. Their outer arms will pass through each other, then swing back, then pass through again. Each pass will disturb the orbits of stars in both galaxies, flinging some out into the intergalactic void, pulling others into new orbits. The tidal forces will trigger bursts of star formation in some regions and disrupt star formation in others. The central supermassive black holes of the two galaxies, the one at the heart of the Milky Way, called Sagittarius I star, and its larger counterpart at the heart of Andromeda, will spiral toward each other over hundreds of millions of years, eventually merging into a single, even more massive black hole. I should note something important here. Recent measurements have added uncertainty to this picture. In 2024 and 2025, researchers using improved data from the Gaia mission and other instruments published analyses suggesting that the classic head-on merger scenario may not be as certain as previously thought. There is now a real possibility, according to some models, that Andromeda and the Milky Way might have a first close pass without a full merger, and might take much longer to fully combine than the original 4 to 5 billion year estimate. Some scenarios have the full merger happening closer to 7 or 8 billion years from now, or in some cases, not happening at all in the way traditionally described. This is an active area of research, and the story is still being refined. What is virtually certain is that the two galaxies will interact gravitationally on a major scale within the next 10 billion years. What is less certain is the exact geometry and timing of that interaction. For our purposes, for Voyager 2, the exact timing does not matter much. What matters is that at some point within the next 10 billion years, the galaxy the spacecraft is orbiting inside of will stop looking like the Milky Way. It will become something else. Some astronomers have taken to calling the eventual merged system Milkomeda, though that name is entirely informal and probably will not survive. Whatever we call it, the resulting galactic remnant will not have the tidy spiral structure of either progenitor. It will more closely resemble a large elliptical galaxy, a puffier, more spherical distribution of stars with less organized structure, less ongoing star formation, and a much more complex history of orbits. Voyager 2 embedded in this system will be riding along on an orbit that gets substantially reshuffled during the merger. This is the important part. During galactic mergers, stars in the outer regions of both galaxies are the most affected. Their orbits get stretched, tilted, and in some cases entirely rewritten by the tidal forces of the interaction. Voyager 2, riding along with the Sun's orbit, or by this point, riding along with what used to be the Sun's orbit, will be subject to those same tidal forces. Its orbital path around the galactic center will change. Whether it ends up on a tighter orbit, a wider one, or a more elongated one depends on the specific timing and geometry of when the merger reaches its neighborhood, and that is precisely the kind of detail that cannot be predicted with any confidence. There's a specific mechanism worth describing here, because it affects Voyager 2 directly. During a major galactic collision, the tidal forces between the two galaxies do not just pull stars around individually. They stretch out enormous streams of material, long ribbons of stars, gas, and dust that get drawn out from the outer edges of each galaxy as the two systems swing past each other. Astronomers have directly photographed these tidal streams in dozens of other merging pairs elsewhere in the observable universe, and they can extend for hundreds of thousands of light years, curling gracefully away from the interacting pair. They are the visible signatures of the merger, more distinctive than the collision itself, and they persist for billions of years after the merger is complete. Voyager 2, riding along with the Sun in the outer disk of the Milky Way, is precisely the kind of object that gets swept into a tidal stream. The Sun is not in the galactic center. It is out in the disk, about 27,000 light years from the middle, in a region that will feel the tidal forces of the merger strongly. When Andromeda approaches, the outer disk of the Milky Way, and everything in it, including the Sun and everything the Sun is dragging along, will get stretched. Some stars will be pulled into a long stream extending in one direction. Others will be flung the other way. The specific outcome for any given object depends on where it happens to be in its galactic orbit. At the moment the tidal forces reach maximum strength, and on the geometry of the encounter with Andromeda. Voyager 2, embedded in whatever tidal stream the Sun ends up in, will be carried along with that flow. Over hundreds of millions of years, the stream will disperse. Some of its stars will fall back into the merged galactic remnant on new orbits. Others will drift far out into the outskirts of the system, or in some cases, escape entirely into intergalactic space. Which category Voyager 2 ends up in is not knowable in advance. But the point is that the merger does not just rearrange the Sun's orbit, it rearranges the entire population of orbits in the outer galaxy, sorting them into inbound and outbound flows, and Voyager 2 is riding along on one of those flows. There is also the matter of dark matter, which we have not mentioned yet, and which is genuinely important for the long-term behavior of everything in the galaxy. The Milky Way's visible matter, its stars and gas and dust, is embedded in a much larger halo of dark matter, a substance that does not emit or absorb light, but interacts gravitationally. Astronomers infer the presence of the dark matter halo from the way stars in the outer galaxy move faster than they should if only visible matter were providing the gravity. The halo extends far beyond the visible galaxy, roughly 1 million light years across, and it contains something like 5 to 10 times as much mass as all the stars combined. When Andromeda and the Milky Way merge, their dark matter halos will merge too. The details of this process are still being worked out because dark matter is very poorly understood. But the general picture is that the combined halo will settle into a new configuration around the merged galactic remnant, and everything in the visible galaxy will be embedded in that dark matter distribution. Voyager 2 will feel the gravity of the merged dark matter halo, just as it feels the gravity of the visible stars, and in fact, the dark matter halo probably contributes more to the spacecraft's long-term orbital motion than any of the visible stars do. The details of the spacecraft's orbit through the merged remnant depend on the specific shape and density profile of that combined dark matter halo, which is another source of uncertainty we cannot resolve. This is one of the two big reasons the trillion-year answer becomes fundamentally uncertain. The other is chaos in the underlying gravitational dynamics, which we touched on earlier. Together, they combine to produce a level of unknowability that is not a failure of measurement, but a genuine property of the physics. Let me try to make the chaos issue concrete, because it matters. The Milky Way, as currently structured, is a collection of a few 100 billion stars, all orbiting a common center of mass, but all pulling on each other gravitationally as they go. Any given star's orbit is not a clean, closed ellipse like a planet's orbit around a star. It is a wobbling, precessing path that is constantly being perturbed by the changing positions of every other star. Most of these perturbations are tiny, but some are not tiny. Every few million years or so, on average, a random star will pass close enough to another star's neighborhood to gravitationally influence it in a measurable way. Not close enough to collide, not close enough to capture, just close enough to nudge. For a coasting object like Voyager 2, these nudges accumulate. Each individual encounter changes the spacecraft's velocity by a tiny amount. Perhaps a few centimeters per second, or a fraction of a meter per second, depending on the geometry of the pass. That is nothing in the moment, but integrate across a billion years, and the spacecraft has experienced hundreds of such nudges. Integrate across 10 billion years, and it has experienced thousands. Each nudge sends the trajectory somewhere slightly different than it would have gone otherwise. And because the outcome of each nudge depends on the exact geometry of that particular encounter, which itself depends on the exact trajectory the spacecraft was on when the encounter happened, the whole system is exquisitely sensitive to initial conditions. This is a technical way of saying that we cannot forecast the spacecraft's specific location a billion years from now, no matter how good our measurements are today. We can describe general statistical properties. We can say the spacecraft is very likely still bound to the galactic remnant. We can estimate the range of orbital radii it is likely to occupy. We can talk about the average frequency with which it will pass near stars. But we cannot point to a specific patch of sky and say, that is where Voyager 2 will be. The physics does not permit that kind of statement across that kind of interval, and we are still only talking about a billion years or so. The question we started with was about a trillion. Between now and a trillion years from now, the composition of the galaxy is going to change dramatically in a different way than the merger. Stars have finite lifespans. Massive stars burn out in millions of years. Sun-like stars last about 10 billion years. But smaller stars, the red dwarfs, which are the most common type of star in the galaxy by a wide margin, can last for hundreds of billions or even trillions of years. Their extreme longevity means that as the deep future unfolds, the population of stars in the galaxy will gradually shift toward red dwarfs. The bright blue stars will die first, in cosmic flashes of supernova and slow gaseous decay. The sun-like yellow stars will follow, ending as white dwarfs. And the small dim red dwarfs will keep burning, mostly steadily, for time periods that dwarf the current age of the universe. By 1 trillion years from now, the galaxy, whatever we are calling the merged remnant by then, will be dominated almost entirely by red dwarfs and stellar corpses. The red dwarfs will still be shining, though many of them will be reaching the end of even their extremely long lifespans. The stellar corpses will be white dwarfs cooling toward black, neutron stars slowly radiating away their heat, and black holes silent and dark. There will be very few young, bright stars. The sky, if anyone could see it, would look nothing like the sky we see tonight. It will be dimmer, redder, and much emptier. Voyager 2, if it still exists in some form, will be moving through this dim, red, aging galaxy. Its orbit will have been shaped by the merger with Andromeda, then by countless close stellar encounters over billions of years, and by the gradual gravitational rearrangement of the galactic remnant as stars have been ejected or scattered. The precise nature of its orbit is unpredictable in detail. In broad terms, though, several outcomes are physically plausible. The most likely outcome, and I want to emphasize that this is a probability statement, not a certainty, is that Voyager 2 remains gravitationally bound to the merged galactic remnant. It will be orbiting the center of that system on some path, possibly quite different from the Sun's original galactic orbit, but still bound. This is the default outcome because escaping a galaxy entirely requires either a lot of initial velocity or a very fortunate close stellar encounter, and Voyager 2 has neither. It is a slow-moving object embedded in a deep gravitational well. The default state is stay in the well. A second possibility, less likely but not negligible over trillion-year timescales, is that Voyager 2 experiences a sufficiently close and well-aligned stellar encounter to gain enough velocity to become weakly unbound from the galaxy. This would happen through a slingshot effect similar in principle to the planetary flybys that shaped the spacecraft's original trajectory back in the 1980s, but with a star instead of a planet. Given enough time, and 1 trillion years is an enormous amount of time, the odds of such an encounter happening at some point are not vanishingly small. If it does happen, the spacecraft could end up on a slow, wide orbit, extending far beyond the main body of the galactic remnant, or in a rare case, on an unbound trajectory that carries it out into the intergalactic void. A third possibility, the rarest of all, is a close stellar encounter that captures the spacecraft, bends its trajectory sharply enough that it becomes bound to another star system. This is extremely improbable, because it requires the encounter geometry to be almost perfectly matched, and because most encounters are too fast and too distant to result in capture. But over trillion-year timescales, extremely improbable events do occasionally happen. It is more likely that Voyager 2 simply passes near many stars over deep time without ever being captured by any of them. But we cannot rule out the possibility entirely. There is another category of gravitational influence that becomes increasingly important on very long time scales, and it is worth introducing before we get to the deepest part of the story. Stars are not the only massive objects in the galaxy. Over billions of years, the population of stellar corpses, white dwarfs, neutron stars, and black holes grows steadily as ordinary stars die. By 100 billion years from now, most of the massive stars that existed at the merger will have long since died, leaving behind these dense remnants. And by 1 trillion years, the population of stellar corpses will dominate the mass budget of the galactic remnant even more thoroughly than it does today. Stellar corpses are still gravitational sources. A 1 solar mass white dwarf pulls just as hard as a 1 solar mass star, and a stellar mass black hole pulls harder because it is more compact and can be approached more closely. Neutron stars and black holes, in particular, can produce very strong gravitational effects during close encounters because a coasting object can pass extremely close to their surfaces, much closer than it could ever pass to an ordinary star, before feeling significant tidal forces. This means that some of the most impactful gravitational encounters Voyager 2 experiences across deep time will be with objects that are, in a certain sense, invisible. A close pass with a stellar mass black hole, for example, could gravitationally scatter Voyager 2 in almost any direction, depending on the geometry of the pass. Such encounters are rare because black holes are compact targets, but over 1 trillion years, the probability of at least one meaningful encounter with some kind of stellar remnant is non-trivial, and each such encounter can significantly redirect the spacecraft's trajectory. There is one more consideration that becomes increasingly important on deep time scales, and it has to do with the chemical evolution of the interstellar medium itself. Over the course of billions of years, the composition of interstellar gas gradually shifts as generations of stars are born, live, and die. Each generation of massive stars synthesizes heavy elements in its core, and each supernova disperses those elements into the surrounding medium. The interstellar medium of 1 trillion years from now will not be chemically identical to the one Voyager 2 is coasting through today. It will contain higher concentrations of heavy elements, more iron, more silicon, more oxygen, more carbon, and the dust grains it contains will reflect that shift. Some regions may become dustier as more heavy elements accumulate. Others may become depleted as gas is consumed by star formation faster than it is replenished. For Voyager 2, this chemical evolution matters because it affects the rate at which the spacecraft's surface is eroded. In a dustier region, sputtering is faster. In a more depleted region, sputtering is slower. The spacecraft's cumulative erosion history over 1 trillion years will depend on the specific sequence of interstellar environments it happens to pass through, and that sequence is itself dictated by its unpredictable orbit. It is one more layer of uncertainty layered on top of everything else. Not enough to change the general picture, but enough to reinforce the fundamental honesty of what we can and cannot say about the far future. What we can rule out, or at least assign very low probability to, is any specific claim about a specific destination. The idea that Voyager 2 is heading toward a particular star, or a particular constellation, or a particular region of space in any deep time sense is not supported by the physics. The spacecraft has a current trajectory. That trajectory can be extrapolated forward for tens of thousands of years with reasonable accuracy, and for hundreds of thousands of years with substantial uncertainty, and for millions of years only in statistical terms. Beyond that, the map dissolves. There is one more phenomenon worth mentioning before we close this part. It has to do with the way the galaxy itself will evolve gravitationally over deep time. Even without the merger with Andromeda, the Milky Way's structure is not permanent. Over billions of years, the process called dynamical relaxation gradually redistributes stellar orbits, ejecting some stars from the galaxy entirely, while causing others to sink toward the galactic center. Over trillions of years, this process becomes profoundly important. Some estimates suggest that on timescales of hundreds of billions to trillions of years, a large fraction of the stars currently in a galaxy will have been ejected through cumulative gravitational interactions, while the remaining stars will have settled into orbits closer to the central black hole. For Voyager 2, this means the environment through which it is moving will be steadily thinning out over cosmic time. Stars will become sparser. The overall stellar density of the region the spacecraft occupies will fall by orders of magnitude as ejected stars leak away into intergalactic space, and the remaining population settles into a smaller central concentration. The spacecraft will still be there, still coasting, still bound in whatever orbit it has settled into, but the sky around it will grow steadily emptier, and the average distance to the nearest star will grow steadily larger. This is the picture at this deeper stage of the story. The Sun is a cooling white dwarf, 5 billion years past its death, sitting somewhere in the galactic remnant. The remnant itself is the merged product of the Milky Way and Andromeda. Its structure elliptical rather than spiral, dominated by red dwarfs and stellar corpses. Voyager 2, 7 billion years past its last transmission, has been reshuffled by the merger and nudged countless times by close stellar encounters. Its exact orbit is unknowable in detail. Its general state is still bound to the galactic remnant, still moving, still carrying its golden record, still silent. The map humanity used to describe where the spacecraft was going has ceased to exist. Not because it was wrong, but because everything that map referred to has moved, transformed, or died. Pavo is gone as a constellation. Sirius is gone as a star. The Sun is gone as a functioning star. The Milky Way is gone as a distinguishable galaxy. And we are still not at 1 trillion years. We are only somewhere around 10 billion years past the current moment. The trillion-year question requires us to keep going for another 99 times as long as we have already gone. And what happens across that further stretch of deep time is where the story reaches its final and strangest stretch. The one where we have to ask not just where the spacecraft is, but whether anything recognizably called a spacecraft still exists at all. That is where we are going next. Before we can meaningfully talk about 1 trillion years, we have to spend a moment sitting with what that number actually is. Because human intuition, honestly, does not have a good handle on it. We have already stretched past 5 billion years for the Sun's death, and past 7 or so billion for the merger with Andromeda, and past 10 billion or so for the reshaping of the merged galactic remnant. Those are all enormous numbers by any human standard. 1 trillion is 1,000 billions. 1 trillion years is roughly 70 times the current age of the universe. The universe, as we currently understand it, from the Big Bang through the first stars, through galaxy formation, through the emergence of Earth and life and human civilization, has occupied less than 1.5% of 1 trillion years. What we are asking about when we ask where Voyager 2 will be at 1 trillion years is a stretch of time so much longer than everything that has already happened in cosmic history that the very concept of a functioning galaxy begins to strain. Let me put it another way. If the current age of the universe were 1 day, then 1 trillion years would be about 70 days. If the current age of the universe were 1 hour, 1 trillion years would be nearly 3 days. If the current age of the universe were 1 minute, 1 trillion years would be more than an hour. The scale is so lopsided that everything we normally consider ancient in cosmic terms becomes recent. The formation of the Sun 4.5 billion years ago becomes something that happened less than 1% of the way through the interval we are trying to describe. The extinction of the dinosaurs 66 million years ago becomes so recent it barely registers. And yet, this is the timescale on which our question is posed. So let us try to answer it as honestly as we can. By 1 trillion years from now, several things will have happened that we can predict with reasonable confidence, and several other things will have happened that we cannot predict at all. Let us take the confident predictions first. The Sun will be gone. Not gone in the sense of destroyed, but gone in the sense of unrecognizable. The white dwarf remnant of the Sun, formed about 5 billion years from now, will have been cooling steadily for the entire subsequent interval. White dwarfs cool through radiation into space, and the cooling process is extremely slow at first. A hot young white dwarf can maintain a surface temperature of tens of thousands of degrees for hundreds of millions of years. But over trillion-year timescales, cooling continues until the object approaches the temperature of the surrounding universe. Current models suggest that after many trillions of years, a white dwarf becomes what is sometimes called a black dwarf, a dark, cold, dense object made mostly of crystallized carbon and oxygen, radiating essentially no light or heat. By 1 trillion years from now, the Sun's remnant will not yet have fully reached that state, but it will be very cold, very dim, and essentially invisible from any meaningful distance. If any observer happened to pass near where the Sun used to be, they would find only a dark, dense sphere about the size of Earth, giving off almost no light. The merged galactic remnant will still exist, but its structure will have evolved further. Star formation will have declined to a trickle. The gas supply that once fueled the birth of new stars will have been mostly consumed, ejected, or dispersed. Most of the massive stars that were around during and after the merger will have long since died. The remaining stellar population will be dominated overwhelmingly by red dwarfs, the smallest and dimmest and longest lived of ordinary stars. Some red dwarfs live for hundreds of billions of years, and the very smallest can survive for more than 1 trillion. So there will still be some genuine hydrogen-fusing stars scattered throughout the galactic remnant at the trillion-year mark, but they will be sparse, cool, and dim. An observer looking outward from anywhere in the remnant would see fewer stars, farther apart, and each one giving off a fraction of the light that a modern sun-like star gives off today. The other members of the stellar population will be corpses, white dwarfs mostly cooling in various stages toward black dwarf status. Neutron stars, still spinning in some cases but no longer bright as pulsars. Black holes, ranging from stellar mass to supermassive, invisible except through their gravitational effects and occasional accretion events. And a huge population of ejected stars and stellar remnants that were kicked out of the galaxy by close encounters during the merger and the subsequent dynamical evolution. Some estimates suggest that by as 1 trillion years, a substantial fraction of what was originally in the galaxy has been dispersed into intergalactic space entirely. This is the environment in which Voyager 2, or the object that used to be Voyager 2, is coasting. Let us now confront the question of whether Voyager 2 is even the right name for that object at 1 trillion years. Because a lot happens to a piece of metal in 1 trillion years. We touched on the erosion mechanisms earlier: dust impacts, cosmic ray damage, sputtering, spallation, Let us think through what those processes do across a trillion-year interval. The rate of dust impacts on Voyager 2 is very low, but the total number of impacts over a trillion years is enormous. If we assume a rough impact rate of, say, 1,000 micron-scale grains striking the spacecraft per year, a rate that is highly uncertain and varies dramatically depending on the density of dust in the galactic region the spacecraft is traversing. Then, over a trillion years, we get on the order of 10 to the 15th impacts. That is a quadrillion tiny craters distributed across the surface of the spacecraft. The cumulative effect over that many impacts is not a light polish. It's a substantial erosion of the outer material. Some estimates in the astrobiology literature suggest that a spacecraft-sized object exposed to typical interstellar dust flux for a trillion years would have its outermost centimeter or so of material sputtered away. Completely gone, atom by atom, redistributed into the surrounding medium. Now, a centimeter is not that much on the scale of Voyager 2's overall structure. The spacecraft is a fairly chunky object. Its main body is a boxy structure over a meter across, with a large parabolic antenna dish mounted on top and various instruments and booms extending outward. If you remove the outer centimeter of material from every exposed surface, you have degraded the appearance and thinned the walls, but you have not destroyed the object. Certain thin components, antenna wires, the delicate mesh of the high-gain antenna dish, the thin metal foil covering certain instruments, would be significantly compromised or eliminated entirely. But the main structural bulk of the spacecraft would still exist. Cosmic ray damage over a trillion years is a different kind of problem. Cosmic rays pass through the entire volume of the spacecraft, not just its surface. Every atom in the spacecraft has some probability of being struck by a high-energy particle over that time frame, and the cumulative damage to material properties can be substantial. Metals become more brittle. Organic materials, if any survived, which is unlikely, break down completely. The polymers that might have been in various coatings, the semiconductor materials in the electronics, the delicate mineral coatings on the golden record itself, all of these are subject to slow but relentless radiation damage. The electronics, of course, stopped working billions of years earlier, so their degradation does not functionally matter. But the physical existence of the components does slowly change. What about the golden record itself? This is the piece of Voyager 2 that has captured the human imagination more than any other component, and it deserves specific attention. The record is a phonograph disc made of gold-plated copper, 12 inches across, engraved with etched grooves containing sounds and images from Earth. It is protected on both sides by an aluminum cover plate. The engineers who designed it estimated its lifetime against interstellar erosion at somewhere between hundreds of millions and 1 billion or more years, based on models of dust flux and cosmic ray damage available in the 1970s. Those estimates were rough. They did not extend to 1 trillion years, because nobody at NASA was thinking about 1 trillion years. If we try to extrapolate honestly, the golden record probably does not survive intact for 1 trillion years. The cover plate protects it from direct dust erosion, but the plate itself is subject to the same erosion, and eventually, over 1 trillion years, the plate probably wears through in places. Once it does, the underlying record is exposed to direct dust impacts, and the etched grooves begin to be worn away as well. The specific timescale for this is deeply uncertain, because it depends on the cumulative dust exposure history of the spacecraft across an unknowable orbit. Best case and worst case erosion rates differ by more than an order of magnitude. But even the most favourable assumption, an orbit that keeps the spacecraft in relatively empty regions for most of the trillion-year interval, still delivers enough cumulative dust exposure to substantially degrade the record. So probably by 1 trillion years, the golden record is not a playable object anymore. The etched grooves have been eroded to the point where the information they carried is no longer recoverable. The message we sent to whoever might find it, whenever they might find it, is gone. The disk itself may still exist as a warped piece of metal, but the content it was designed to carry has been erased. It is worth zooming out for a moment here, because the trillion-year mark, enormous as it is by any human standard, is not actually the end of any physical story. It is more like an early chapter in a much longer physical future that cosmologists have started trying to map. There are physical processes that operate on timescales so much longer than 1 trillion years that they make the trillion-year interval look almost brief. The smallest red dwarfs, for example, will keep burning for something like 100 trillion years before finally exhausting their hydrogen, 100 times longer than the interval we are trying to describe. The gradual gravitational dissolution of galactic remnants, in which cumulative stellar encounters eject essentially all remaining stars into intergalactic space, happens over timescales of somewhere around 100 quintillion years. That is 100 billion years. A number so large that 1 trillion years fits inside it 100 million times. And if certain speculative theories of particle physics are correct, protons themselves may eventually decay, with the last atomic matter in the universe dissolving over timescales that might reach a duodecillion years or more. Though this process has never been experimentally observed and remains hypothetical. What this means for Voyager 2, specifically, is that the atomic composition of the spacecraft is essentially stable across the interval we are asking about. The aluminum atoms in its structural walls, the gold atoms on its antenna surface, the copper atoms in the golden record, none of these are going to spontaneously decay into other elements on 1 trillion-year timescale in any measurable way. The atoms will still be atoms, the metals will still be metals. Whatever destroys or degrades Voyager 2 across 1 trillion years will not be atomic decay. It will be mechanical in the broader sense, dust impacts, cosmic ray damage, sputtering, and possibly rare catastrophic collisions with larger objects. The chemistry stays intact. Only the arrangement of matter suffers. This is a strange thing to acknowledge. In one sense, 1 trillion years is unimaginably long enough to erode the golden record beyond recovery, long enough to reshape the galaxy the spacecraft is embedded in, long enough for our sun to have died, cooled, and dimmed toward black dwarf status. In another sense, 1 trillion years is short enough that ordinary matter is still ordinary matter, that many of the smallest red dwarfs are still burning, that the truly late epochs of the universe have barely begun. Voyager 2, at 1 trillion years, exists in a peculiar temporal position. It is old beyond any human capacity to comprehend, and yet, on the deepest physical timescales, it is still relatively young. There is still much more cosmic time ahead of it than has passed since its launch, even at that immense interval. The spacecraft, if it survives at all, has traveled only a small fraction of the way into the physical future that theoretically remains. The rest of the spacecraft is in similar condition. The high-gain antenna dish, once a shining parabola nearly 4 meters across, is probably a warped and eroded skeleton, its mesh degraded and its shape compromised. The main body may still be roughly intact, but its walls are thinner, its exposed edges are pitted, and any distinguishing surface features, the markings identifying different subsystems, the small plaques with mission information, have long since been erased by the cumulative pitting of dust impacts. Whether an outside observer could identify this object as a manufactured artifact at all is a real question. If some hypothetical civilization somehow came across the spacecraft at the trillion-year mark, what would they see? They would see a car-sized piece of metal, roughly boxy in overall shape, with various protruding structures that might be recognizable as antennas and instrument booms, all severely eroded and pitted. The metal composition would still be identifiable as artificial. The specific alloys used, the presence of elements like titanium and aluminum in specific ratios, the traces of gold on the surface, would all be strong signatures that this object did not form naturally. So yes, it would probably be identifiable as an artifact, if anyone happened to examine it closely. But whether anyone will ever examine it closely is a completely separate question, and one we cannot answer at all. Let us now try to answer, as best we can, the question the title actually asks. Where will Voyager 2 be at 1 trillion years? The honest answer requires talking about probabilities rather than coordinates. Given everything we have discussed, several outcomes are physically plausible, and each carries some probability of being what actually happens. We cannot pick one and say, this is where the spacecraft will be. The most we can do is describe the range. The most probable outcome is that Voyager 2 is still gravitationally bound to the merged galactic remnant. It is orbiting the center of that system on some path, deep inside what used to be our galaxy plus Andromeda, combined into a single elliptical structure. The specific orbit is not predictable. It could be a relatively tight orbit, in which case the spacecraft passes near the central regions of the remnant every few 100 million years. It could be a wider orbit, in which case the spacecraft spends most of its time out in the sparser halo of the remnant. It could be an eccentric orbit that swings between the two. What we can say is that the spacecraft is somewhere in the general vicinity of the merged galactic remnant, still coasting, still obeying gravity and inertia, still moving. A second, less probable outcome is that at some point during the trillion-year interval, a sufficiently close and well-aligned stellar encounter has knocked the spacecraft onto a trajectory that carries it out of the galactic remnant entirely. This does not require the encounter to be dramatic. It just requires the gravitational geometry to be right. And given 1 trillion years of opportunities, the probability of at least one such encounter is not negligible. If this happens, Voyager 2 ends up in the intergalactic void, coasting along at whatever velocity the encounter gave it, potentially never encountering another star or galaxy for the rest of cosmic history. The spacecraft becomes, in effect, a piece of intergalactic debris, unbound from the galaxy that birthed it, and drifting freely through the space between galaxies. A third, even less probable outcome is that the spacecraft has been captured by a stellar system. This requires a very specific and improbable encounter geometry, a slow, close pass with a star or stellar remnant that redirects the spacecraft's trajectory sharply enough to bind it gravitationally to that new system. Most stellar encounters are too fast and too distant for this to happen. but over 1 trillion years of opportunities, the odds are not exactly zero. If it happens, Voyager 2 ends up orbiting some other star or dead stellar remnant, effectively adopted by a new gravitational parent. Whether that parent has planets, whether those planets are habitable, whether any observer exists in that system to notice the spacecraft, all of these are separate questions with their own vanishing probabilities. The most we can say is that capture is possible, but very unlikely. And there is a fourth outcome, which is that the spacecraft has been destroyed. Not by a single dramatic event, but by the cumulative effects of erosion, radiation damage, and possibly a direct collision with a rare, larger dust grain or small rocky body. Over 1 trillion years, the probability of some kind of catastrophic collision is small, but not zero. Particularly if the spacecraft's trajectory takes it through dense regions of the galaxy, or through the dense material near stellar remnants. If such a collision has occurred, then what remains of Voyager 2 is a scatter of fragments, dispersing slowly along the original trajectory, still recognizable as pieces of manufactured metal if closely examined, but no longer coherent as an object. Of these 4 outcomes, the most likely by a substantial margin is the first. The spacecraft is still bound to the galactic remnant, still coasting, still obeying gravity. The other outcomes are all possible, but each carries lower probability. And within the first outcome, the specific orbit and location of the spacecraft is not predictable. We can say it is somewhere in the general vicinity of the merged galactic remnant. We cannot say more. Notice what this means. The answer to where is Voyager 2 at 1 trillion years is not a coordinate. It is not a star or a system or a specific region of the sky. It is a probability distribution across an enormous and increasingly dispersed volume of space. And every reference point we might have wanted to use to describe that location, the sun, the constellations, the Milky Way itself, has either transformed beyond recognition or ceased to exist as we currently know it. This is why the question the title asks is fundamentally different from questions we ask about ordinary trajectories. When we ask where a satellite in Earth orbit will be tomorrow, we could compute the answer to within a few meters. When we ask where a spacecraft on its way to Jupiter will be in 5 years, we can compute the answer to within a few kilometers. When we ask where Voyager 2 will be in 100,000 years, we can give a probability distribution that spans maybe a light year. When we ask where it will be in 1 billion years, the distribution spans thousands of light years. When we ask where it will be in 1 trillion years, the distribution effectively spans the entire volume of the galactic remnant and possibly the intergalactic space nearby. The physics does not permit a more specific answer. It is not a matter of measurement precision. It is a matter of chaotic dynamics compounding across immense time. Let us now step back and try to see what all of this actually means. Voyager 2, in the 20th century, was launched with a specific and carefully designed purpose. It was aimed, refined, corrected, and commanded across decades to complete a grand tour of the outer planets, and then to sail outward into interstellar space, carrying a message from Earth. Every detail of its early life was shaped by human intention. Its trajectory was chosen. Its instruments were designed. Its golden record was carefully curated. It was, in the truest sense, a designed object, a piece of technology that reflected the ambitions and values of the civilization that built it. But designed objects, when released into deep time, do not stay designed. They become, over long enough intervals, indistinguishable from natural objects except in their material composition. The trajectory that was carefully chosen becomes a coasting motion at the mercy of gravity and chance. The instruments that were carefully engineered become inert lumps of eroded metal. The message that was carefully curated becomes a worn disc whose grooves have been polished away. What is left is not a spacecraft in any functional sense. It is a piece of matter with a specific origin story that no longer exhibits any of the properties by which we would normally define its category. By 1 trillion years from now, Voyager 2, if it still exists, is a piece of very old, very worn metal drifting through a very old, very worn galaxy, carrying no functional message, receiving no signals, sending no signals, obeying no commands. It has become what one might call cosmic archaeology. It is a relic. Its meaning, if it has any meaning at all, comes only from the fact of its existence. The fact that at some ancient moment in the far past, a civilization existed that chose to build such an object and send it outward. Everything about that civilization is long gone. Its planet, its star, its language, its species, none of these things exist anymore in any recognizable form. The spacecraft is the only physical trace left, and even the spacecraft is a shadow of its original self. This is the honest answer to the title question. Where will Voyager 2 be at 1 trillion years? Somewhere in what used to be our galaxy, probably. Coasting along an unpredictable orbit. Eroded, but likely still recognizable as an artifact. Carrying an unreadable message. Silent. Purposeless in any operational sense. And still moving. The deeper implication, and this is where I want to leave you, is that Voyager 2 is doing exactly what every physical object in the universe does when nothing constrains it. It is obeying gravity and inertia. It is not accomplishing a mission. It is not reaching a destination. It is not delivering a message. It is simply continuing to exist in motion because motion is what it was given at launch, and nothing has fundamentally taken that motion away. The spacecraft outlives its own purpose, and it keeps going anyway, because the physical universe does not care about purpose. There is something both humbling and clarifying about this. Humbling, because it puts into perspective what we can and cannot achieve as a civilization. We can build objects that outlast us, indeed, that outlast our star, our galaxy, and possibly every other structure we would recognize. But we cannot make those objects mean anything past a certain point. Meaning requires an audience, and audiences do not last forever. The golden record was designed as a message to whoever might find it, and that design assumed there would be a finder capable of understanding the message. Over 1 trillion years, the probability of such a finder existing and encountering the record is vanishingly small, and the physical medium carrying the message will have been eroded past recovery long before then anyway. Clarifying, because it forces us to acknowledge what a mission actually is. A mission is not a permanent property of an object. A mission is a relationship between the object and the people who care about it. When those people are gone, the mission is gone. What remains is just the object, obeying physics. Voyager 2's mission ended in the 20th century, when the primary planetary encounters were complete. Its extended mission will end in the 2030s, when the last transmission fades. Everything after that is not mission. It is physics. It is a piece of metal doing what metal does when you give it velocity and set it loose in a gravitational field. And yet, and this is the strange consolation of it, the object does keep going. long after we are gone, long after the sun is gone, long after the Milky Way is gone, long after the very concept of years measured against Earth's orbit around the sun has ceased to make sense. Voyager 2 keeps coasting, unaware that it is coasting, embedded in a galaxy that no longer resembles the one it left. The trajectory is not toward anywhere in particular. There is no destination. There is only motion and gravity and time, and the slow, patient work of dust and radiation reshaping the object atom by atom across intervals so long they defy comprehension. We can predict, honestly, that Voyager 2 will continue to obey gravity and inertia. We can predict that its motion will not stop until something acts on it, and that in the deep future, almost nothing will act on it in any significant way. We can predict the general shape of the environment it will pass through. We can even predict, roughly, what 1 trillion years of erosion will do to its surface. But we cannot preserve the map around it. We cannot name a star it will visit. We cannot promise anyone that anything will ever find it. And we cannot make its journey mean anything past the horizon of our own civilization. 1 trillion years from now, the spacecraft may still be traveling, but nearly everything humanity currently uses to explain where it is, every constellation, every star, every galactic feature, every coordinate we would recognize, will have vanished. That is the honest answer. It is not the answer we might have wanted. It is not a triumphant arrival or a sentimental reunion. It is just physics, continuing after we are done watching in a universe that keeps moving without us. Voyager 2, in that far future, is not a spacecraft anymore. It is a piece of the past, drifting through what used to be our galaxy, obeying laws that predate humanity and will outlast it, going nowhere in particular forever.